All right. Good evening to you all. All right, you're welcome again. To the physics 142 tutorial. The other time we're considering something on atomic physics. All right. So this is just a continuation on it. So we have been able to look at the J.J. Thomson's experiment, the John Dalton's experiment, which was the first experiment we considered. With I've applied five different things in that place, and we're also able to see the J.J. Thomson's experiment, which talks about the discovery of the charge to mass of an electron and the cathode ray. I said that cathode ray are fast-moving electrons which are produced in cathode ray tubes, and I was trying to mention some of the properties of cathode ray in the first video. So I said that they travel in a straight line. All right, that's one of the property. Another property is that they are fast moving electrons. That's number two. They are deflected in electric and magnetic field. So I said they are particles. If you listen very well in the first video, they are particles. That means they possess energy and momentum. So they move towards the positive plate. That means they are negatively charged. All right. So you can use those as the properties of cathode ray. So all of the outline in the first video. All right. We talk about the five experiments of five John Dalton's postulation. All right, from atom is the smallest individual particle of an element, and we have seen the modification, the postulation and the modification. So the next thing, all right, we considered was the J.J. Thomson's, which I think we derived like three equations. The first one was E over M is equal to, I think we have GD over V, all right. So this was the first, when an electron is moving, all right, into an electric field. All right, I said if the electric force or electromagnetic field, if the electric force is balanced with the magnetic field, there's not going to be deflection, but if it's not balanced, there's going to be a deflection. So we had the first value to be this, okay, from our FA is equal to FB, and I told us that FA is equal to EQ, all right, then your FB is equal to BQ and the like. So now this was for the first theorem, but for the second theorem, all right, I said the electron is entering into a circular field, all right. So we had two different, like three formulas. The first one was E over M is equal to, I think we have V over BR, all right, if you remember. And I said that V is equal to omega R. So we have E over M is equal to, anywhere you see the value of V, you now write as omega R over BR. So if that's the case, E over M is equal to, so R is going to go with R. So you have omega over B. So this R, this one has gone. Then this E over M is equal to omega over B alone. So we have E over M, which is charge to mass, is equal to the value of omega. Omega is equal to 2 pi F, right, in circular motion. Right, so well, because this electron is entering into a circular magnetic field, that's why we're using centripetal force. So which is the value of omega we have in that place. Then we have 2 pi F divided by, so your B is the magnetic field intensity. So this is what your charge to mass in this charge to mass in terms of the what of the frequency. This one is in terms of the angular velocity. Right. So then the last one, right, we said that our frequency, all right, frequency F can be equivalent to 1 over period. Okay, so if F is equal to 1 over period, so we recall E over M is equal to 2 pi F over B. Okay, so what is the value of F? F is now 1 over T, so you have charge to mass of an electron is equal to 2 pi multiplied by 1 over B, then you have T here. Alright, so at the end you have charge to mass is equal to 2 pi over the magnetic field intensity multiplied by period. So this E over M, alright, for the first postulation of first theory of J.J. Thomson's, this is the charge to mass of the electron, gravity multiplied by distance apart over the velocity, alright, sorry, that velocity, voltage rather, potential difference. Then the second, alright, when the electron, this one is when the electron is entering into an electromagnetic field. But the other postulation, so we had one equation in that place, but here we have like three equations. This is the first equation, this is the second equation, equation number 2, and this is the third equation, equation number 3. All right, so this one is when the electron is entering into an electromagnetic field, while this one is when the electron is entering into a circular magnetic field. So we have three different things there. E to M for the first one, E to M, which is charge to mass equal to G over V, when the electron is entering into an electromagnetic field. But when it's entering into a circular coil, so we have three equations. E over M is equal to omega over B, magnetic field intensity times mass. E over M, all right, is equal to 2 pi f over b, which is b is the value of the magnetic field intensity and f is the frequency. Then we have the value of period here. E to m, charge demand is equal to 2 pi over magnetic field intensity multiplied by the period, all right, of the material. So, all right, of the particle. So that's what we have for the first experiment. Then we move to the next two. So the next two experiments, that's we can don't forget that I mentioned the properties of cathode ray. I said they move they move in straight line. Alright, so the direction is straight and they are negatively charged. They move towards the positive plate, which suggests that they are negatively charged. And the next one we said that they possess energy and momentum, which suggests that they are particles. Alright, and we also said that they can be deflected, alright, or they are deflected in electric and magnetic field. Alright, so once we are done with J.J. Thomson's experiment, we are done with John Dalton, and we are done with J.J. Thomson. So the next scientist we want to consider, John Dalton, we have considered it, alright, in the first video, and we have done J.J. Thomson, alright, also have been treated in the first video, which I have done recap for. Then the next person is who we call Ernest Rutherford. So what was Ernest Rutherford's contribution to this? So I'm not going to outline the calculation, but Ernest Rutherford, alright, now you must have known before that, alright, you have here the center is what we call the nucleus, alright, and also the proton. Then your electron actually revolves around the what? Around the nucleus. Okay, so if the electron revolves around the nucleus, okay, so what was Rutherford's contribution? So you can write it down or note it down so that you know. Rutherford actually says that his postulation goes thus: as electron revolves around the nucleus, okay, we can say that Ernest Rutherford explained that the protons are located at the center of the atom, alright, which is called the nucleus. Ernest Rutherford explained that the protons are located at the center of an atom, which is called the nucleus, while the electrons revolve around the nucleus as planets revolve around the sun. That is Ernest Rutherford experiment, alright. He says he explained the fact that protons are located at the center of the atom, right, called the nucleus, and the electron revolves around the nucleus as the planet revolves around the sun. Alright, now what was his contribution or his postulation? But the limitation to his experiment is that his experiment actually suggested the short lifespan of an atom. Alright, because as the electron moves around the nucleus, alright, it eventually radiates energy and it collapses inside the nucleus. Alright, so the limitation to his postulation is that his postulation suggests the word short lifespan. Alright, short lifespan of what? Of an atom. Short lifespan of an atom. That is his limitation. Then, aside from that, Neil Bohr now continue from that place. Alright, Neil Bohr continue from where that. So that is the postulation and that is the limitation. Then, if you want to look at Neil Bohr's experiment now, this is where the major thing is. Alright, so we have Neil Bohr. Now, for Neil Bohr, I'll first of all outline, alright, his theorem. Then after that, we'll now see some of the calculation and some of the things he did as a calculation and proof. Now, what is Neil Bohr's experiment? His experiment is based on hydrogen atom. Okay, so his first postulation is that electron revolve around the nucleus in definite part called shell. That is the first. Electron revolve around the nucleus in definite part called shell. We are going somewhere. Then the second postulation from Neil Bohr, he said the angular momentum of this orbit or shell is quantized. Alright, so when you talk about quantum, alright, or quanta is talking about, or quantum is talking about, quantum is talking about packet of electrons. Alright, so he says the second position says that the angular momentum of this orbit shell is what is quantized. That means they can occupy a certain energy, alright, which is assigned integral value. So the angular momentum of an electron, according to Neil Bohr, alright, we have NH, we have NVR, NV is the angular momentum, okay, is equal to NH over 2 pi, right? This, or we also use this in Heisenberg law of uncertainty. So we have NVR is equal to what? NH over what? Over 2 pi. So this is the angular momentum. In case, right, you are asked, NVR is equal to N open bracket H. H is the Planck constant over 2 pi. So if that is the case, all right, so what's going to be the next thing? So the next thing is to actually see the third theorem. So once that formula has been noted, of course we know that our n here is the number of shells, m is the mass, v is the velocity, r is the radius, alright, then h is the Planck constant, and Planck constant is 6.63 times 10 raised to the power minus 34. So, and our number of shells starts from 1, alright, 2, alright, 3, 4 to what? To infinity, or 3 to infinity, alright, that's the number of shells of the what? Of the atom. Quite important. So if that is gotten, let's move to the third postulation. And you're also to note that your n, alright, is KLMN. KLMN, alright, that's what you have at the what? At the shell. It will get like that from 1, 2, 3, then you have what? N to be what? KLMN. Alright, so aside from that, now when you move to the third theorem, now the third theorem says that at a particular energy level, electrons do not radiate energy, alright, but radiation occurs when electrons move from one shell to another. So there is a tendency for an electron to move from one particular shell to another. Must have done that in chemistry. Wow, bond, alright. So then this is my interest. Now the fourth and the fifth postulation, this is the third, alright, that electron can jump from one shell to another. But the fourth and the fourth shows actually the emission and the absorption of an electron. So now when an electron jumps from one energy level to another energy level, now if it's from a lower energy level, alright, to higher energy level, now what is going to happen is that there's going to be absorption of electron. Okay, absorption of electron if it's from lower energy level to higher energy level. But if it's jumping from higher energy level, alright, to lower energy level, there will be emission of electron. Alright, so the fourth theorem says that when an electron jumps from the third says that shell, alright, electron move from one shell to another, but the fourth says that when an electron jumps from a lower energy level to high energy level, there is an absorption of electron. Why if an electron jumps from high energy level to low energy level, there is an emission, alright, emission of what? Of electrons. So those are the two different categories of things you have in the concept. So that is how to go about Niels Bohr's experiment. So now let's now look at the mathematical things, alright. Now, but if I want to restrict this to the question they can ask, alright, basically the first question they can ask is they can ask to determine because here the concept is actually to determine the energy of an atom, the radius of an atom as well, radius of an atom, and the energy of an atom. These are the two basic questions, right, that they basically ask, right? So you have energy of an atom and the radius of an atom. So the first thing we want to consider is the radius. Now, what Bohr did, alright, Bohr actually balanced an electric force with also what we call a centripetal force. Alright, so I'm not going to do the proving, or let me go into the proving so that you understand analytically how it works. Okay, now but if you are to determine the radius of the atom, alright, just use your arm. Radius of the atom is equal to n squared over z all into r naught. Okay, this is how to determine the radius of an atom according to the Bohr's experiment. It has proven, but we're not going to go into that. But if you have to determine the energy of the electron, use energy is equal to minus 13.6 eV, right, over n squared. Okay, so this is for calculating radius of an atom. This one is for calculating the energy of an atom, alright? And that 13.6 can have z, alright? You can also use E is equal to minus 13.6, right? Z squared, then EV over what? Over n. Alright, over n squared. Okay, so you can use any of those two formulas to calculate for energy and for radius, alright, of an atom. So you can use that to determine it.